All right, everybody. Let's talk about how we can put some numbers onto these force problems. Now, we'll have to start by doing a little bit of vocabulary about mass. There are two masses, a gravitational mass and an inertial mass. And we need to define them because we're going to be concerned about what the mass of our object is when we are applying forces to it. So first what we're going to do is we're going to talk about what is inertia. Inertia is the tendency for an object to keep doing what it's doing. If the object is moving, it's going to want to keep moving. If that object is at rest, it is going to want to stay at rest. That quality of kind of want to continuing to do whatever it is that the object is doing, we call the inertia of the object. Now, we don't calculate inertia. It's more just a property that we think of. Now, that does help us think about this inertial mass, though. We can find the inertial mass of an object by using Newton's second law. So this inertial mass is the mass that is calculated using Newton's second law. Now, we have not yet talked about Newton's second law, so you probably don't have a strong idea of how you would calculate the inertial mass of an object. And don't worry, we'll get there. We just don't need to get there today. Now, this is in contrast to a gravitational mass. And gravitational mass is what we've been using on your first homework assignment, okay? Because gravitational mass is the mass that is calculated using that equation that we came up with in class last time, Fg is equal to mg. So if you're ever using this little Fg formula, you're using the gravitational mass. Now, the question is, what's the difference between gravitational mass and inertial mass? And, well, as far as current science can tell, there is no difference. Nothing. Now, that doesn't mean that that might change in the future with future scientific experiments, but the scientific experiments that we have done so far show that there is no difference between gravitational mass and inertial mass. Okay, let's now actually talk about being able to put numbers onto these force problems, okay? Now, we know from Newton's first law that for an object to be at rest or for it to be moving at a constant velocity, our forces have to be balanced, okay? And what do we really mean when we're saying that? When we talk about balanced forces, we're really just trying to describe the fact that when we are at rest or moving at a constant velocity, our forces will cancel out. Okay, any force that is pulling us to the right is offset by a force pulling us to the left, and any force pulling us up is offset by a force pulling us down. And we can write that mathematically by writing that the sum of forces in the x direction has to be 0. Okay, that Greek letter sigma means sum of, okay, and we need to have the sum of our forces in the y direction be 0 as well. Okay, that's what it means for forces to cancel out. It's what it means for forces to balance. So if we want to look at an example of that, we'll just do a real simple example. We'll do somebody who's pushing a box across a rough floor. And, well, here's our box. It's going to be a gigantic box, okay, because here's our person pushing this box along. So if we're interested in this box here, Then we can draw the force diagram for this box. And the force diagram would show that there is a force of gravity pulling the box down. There is a normal force from the floor pushing the box up. I'm going to say that this person is pushing, so they are pushing to the right with an applied force. Because this box, I think it's, what did they say? It's moving at a constant velocity. So we know that there must be some kind of force that is pushing to the left, and it must be friction trying to stop this box from moving. Okay, so what can we say about the forces that are acting on this box? Well, we would be able to say that these forces all have to cancel out. Now, we could write that like a little equation, okay? We could write and say, hey, you know, all those forces that are in the x direction, they gotta add up to be 0. So what forces are we talking about? We're talking about the applied force, and we're talking about the force of friction. So when we add that applied force and that force of friction together, we would expect that it equals 0. In the y direction, what forces do we have? Well, we have that force of gravity, we have the normal force. And so we would expect those forces to sum to be 0 when we add the two of them together. Okay? So what we can do then is using these two equations that we've written, these little sum of forces equations, we can actually solve for these forces, okay? Let's do one more example where we write out the force equation, and then we'll actually put some numbers to it. So here's a problem where we've got this car, it's stuck in a snowdrift, Ruby's pushing on the car. I've drawn the situation over here. Now, why this person is pushing the car into the snowdrift is anybody's guess, but we'll just kind of go with it. Now, if we look at this car, we know that there will be a force of gravity pulling down on the car. We know that there will be a normal force from the ground pushing up on the car. We've got Ruby. She is pushing the car to the right for whatever reason. Maybe it's her brother's car. She got mad at him. Anyway, but she has an applied force that is to the right. And then we have the snowdrift, which is pushing back to the left, right? So that's another applied force. So when we want to think about what forces are acting in the x direction, our forces in the x direction is the applied force due to Ruby and the applied force due to the snow. And when you add those two together, they should add up to be 0. In the y direction, we've got the force of gravity. Oops. Ooh. Sorry, guys. I totally crashed the app. Okay. Here we go. What did we say? We said the forces in the x direction were the applied force due to Ruby and the applied force due to the snow. And then, yeah, this is where we were. Our y forces are the force of gravity and that normal force that was pushing up. Okay, so let's now let's look at a new problem. Let's write some force equations and then use those force equations to actually solve for some quantities of forces. So what we have here is we've got a mass, and it's hanging from two cables. Okay, one cable is pulling straight to the right, the other cable is pulling up and to the left at an angle of 25 degrees from vertical. So since we're interested in this mass, we're going to draw the force diagram for this mass. And this mass has a force of gravity pulling down on it. We've got tension in cable 1, which is pulling us to the right. And then we've got the tension in cable 2, which is going to be pulling us up and to the left. Now remember, the thing about cables is that they can only pull in the direction that they are pointed. So our first cable has to go straight to the right, our second cable has to go up and to the left in the same direction as the cable. So when we look at this, it may not be totally obvious to us that these forces are going to balance out, but they will, or it will become more obvious to us that they will, if we take this tension in the x direction and we break it up into its components, right? We break it up into its x component and we break it up into its y component. Okay? Because that x component we know should cancel with the first tension force. And this y component we would expect to cancel with that force of gravity. Ooh, that deserves 2 lines. So we're going to have to use our knowledge of components in order to help us solve this. And we're good at that because we did that in the previous unit. Okay? As long as we know this angle, they tell us that this angle right here is 25 degrees. And we know at least one side of our triangle, we should be totally good to find all other sides of the triangle. So what we're going to start with is we're going to start with writing out that force equation. We'll start with the x direction. So what are all the forces that are just acting in the x direction? Well, tension in cable 1 is just acting in the x direction. And then part of the tension from cable 2 is just pulling in the x direction, right? It's the x component of this. And I can find the x component of FT2 by doing FT2 times the sine of 25, right? Because this angle right here is the 25, and if I want to find my x component, I am opposite that angle, which is why I need to use sine in order to find my x component. Now I can do the same thing for the y dimension. We can say all of our forces in the y dimension are equal to the force of gravity, right? Because all of the force of gravity is in the y dimension. And then sum of FT2 is in the y dimension, right? It's the y component. We can find that y component by taking FT2 times the cosine of that 25 degrees, since that y component is adjacent to our 25 degree angle. So we can use this information to find the tension in the two cables. Now, I kind of covered it up here, but not only do we know that there is a 25 degree angle, but we also know that this box has a weight of 100 newtons, okay? This is trying to tell us what our force of gravity is, because weight is a synonym for the force of gravity. So if I want to find the tension in the two cables, since I know that the force of gravity is 100, I can use that along with Newton's first law to figure out what our tension in FT2 is. So I'm going to rewrite that force equation. Forces in the y direction are the force of gravity plus the y component of FT2. Now, according to Newton's first law, right, for this object to be at rest, those forces have to sum to 0. Okay, so our total forces in the y direction have to be 0. The force of gravity is 100 newtons, and that's pointed down, so I'm going to call that a negative 100 newtons. And then ft2 is an unknown to us. We got that cosine of 25. So when we look at this, the only thing we do not know is this ft2. And we can solve for that algebraically, right? We add 100 newtons to the other side to get that 100 is equal to ft2 cosine of 25. And then we divide both sides by the cosine of 25, and we find that the tension in cable 2 is going to end up being 110.3 newtons. Which is great, right? We've successfully used our force equation to actually solve a problem. Now let's find the tension in the second cable, and that would be ft1, and we can use our x force equation to find the tension in cable 1. So I'm going to rewrite that force equation. Forces in the x direction are ft1 plus the x component of ft2, which was ft2 sine of 25. Again, Newton's first law tells us that these forces have to sum to 0. So we'll have 0 equals ft1 plus, now since the y component of ft2 is pointed to the left, I'm going to call it ft2 a negative 110.3. That way I'm getting that leftward direction in there. Okay, and when we take 110.3 times the sine of 25, we end up getting 46.6 newtons. And so, therefore, we know that the tension in the first rope has to be 46.6 newtons. Okay. Let's try another example problem so that we can get more practice doing this. Now, if you notice, this next example problem is the exact same situation as the previous example problem. We still have two ropes, we still have a mass, one rope is pulling to the right, and one rope is pulling at 25 degrees left of vertical. And so, since this is the exact same scenario, we are going to have the exact same force diagram. Right? This is the exact same force diagram as the previous problem. Now, because we have the exact same force diagram, our force equations are going to stay the same, right? Because force equations just come from our force diagram. That's how we wrote these two previous force equations. We wrote them by looking at our force diagram. So I'm going to copy these and paste them here, since they should stay exactly the same given the same force diagram. Now, the thing that is different in this problem is that we no longer know the weight of our box, right? There is no longer 100 newtons here. Instead, the thing that we know is we now know ft1. Okay, so this is the quantity that we know, and we now want to find out what is ft2 and what is that force of gravity. So, actually, we just want to find the force of gravity, right? Because remember, weight is a synonym for the force of gravity. Now, I think I will have to find ft2 in order to find that force of gravity, because given that my only known right now is ft1, I only know stuff in the x direction. I know nothing in the y direction, so I can't directly solve for the force of gravity. Instead, I think I'm going to have to find, ft2, and once I know ft2, I should be able to solve the problem and find the weight of our box. Okay, that'll be our plan of attack for this one. So we're going to start with all the forces in the x direction, which is Ft1 plus Ft2 sine of 25. So Newton's first law says that these forces should sum to 0. So we got 0 is equal to 100 newtons plus Ft2 sine of 25. And if we do the algebra, and I know you guys are so good at algebra, so I'm sure that you can do this, and find that the tension in our second rope should be 236.62 newtons. And I'm not going to worry right now about whether or not that's a positive or a negative, because the force diagram tells me about whether or not things should be positives or negatives, okay? And Ft2 right now, we don't have to worry about that. Instead, what we need to do is we need to now use our y force equation, which is the force of gravity plus the y component of Ft2. And Newton's first law says that this will sum to 0. And this is where I need to worry about positive or negative for Ft2. Now, when I think about the y component of Ft2, that component is being pulled up. So I'm just going to keep Ft2 as a positive 236.62. And now solve the problem. And when you solve this, you find that the force of gravity must be negative 214.5 newtons. And that negative sign makes sense, right? Because the force of gravity is pulling down. So I think we did those positives and negatives correctly. Now, to finish today, we're going to do one last example of forces acting at an angle. We're going to do one that's slightly different. Okay, it's not a sign hanging from ropes anymore. It's now a guy pulling on a wagon. So we've got this wagon here that we are very interested in. And if we draw the force diagram for the wagon, we see some pretty interesting stuff. First, we see that there's a force of gravity pulling down, and we know that the ground has to be pushing up. So there's a normal force here from the ground. Now, the what is it? Guy? Girl? The name is Sam, so I guess it's a little ambiguous. But Sam is pulling on this wagon at an angle of 45 degrees. So we're going to have to show an applied force that is pulling at that 45-degree angle, okay? Because forces are going to be in the direction of the push or the pull. So this force is not straight to the right, it is at that 45-degree angle. And we can read from the problem statement that the wagon's not going to move, so there must be another force acting on this wagon to keep it from moving. That must be the force of friction. Maybe these wheels have rusted over or something like that. Okay, so this force diagram is a little bit different for us. It's one that we haven't necessarily seen before. Now, what we are asked to do is we are asked to calculate that normal force and calculate the force of friction. And we can easily do that by writing out some force equations and solving. So let's start by maybe finding the normal force, right? So we're going to start by finding our normal force. And the normal force is acting in the y direction. So we're going to want to write a little equation that describes all the forces acting in the y direction. And that would be, the normal force and the force of gravity and part of the applied force from Sam, okay? Not all of it, not all of it. It's just the y component of this applied force from Sam. So if we actually show those little x and y components, we see that our 45-degree angle must lie right there. This is our x component, this is our y component. And we can calculate that y component of the applied force from Sam by doing FA times the sine of 45 degrees, since the y component is opposite the 45-degree angle that we know. So according to Newton's first law, these forces need to sum to be 0. So 0 is equal to the normal force plus the force of gravity, which they tell us is 500 newtons, right? Because we know that weight is synonymous with the force of gravity, and that force of gravity is down, so we're going to put negative 500 newtons in for that force of gravity. Now we know that Sam is pulling with 150 newtons at an angle of 45 degrees. So when we look at this force equation, the only thing we don't know is the normal force. And when we do the algebra, we find that that normal force is going to be 394 newtons. Not too bad. Now let's find the force of friction. Right? Now that we have found the normal force, let's find the force of friction as well. Can I? Oh yeah, there we go. That's how you make it smaller. All right. So, force of friction. The force of friction is occurring in the x direction. So in order to find this force of friction, we should write a little equation for all the forces in the x direction. And that would be the force of friction and the applied force from Sam, but only the x component of the applied force from Sam. So it'd be FA cosine of 45. And again, Newton's first law tells us that these forces must sum to 0. So, let's see, Sam is pulling to the right, so we'll call that the positive direction. We'll make this a positive 150 cosine of 45. And when we do the algebra, we find that this force of friction must be 106 newtons. All right. Success! We now know how to write force equations and use those force equations to actually find the values of various forces acting on an object.